Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been discussing a very important and interesting topic over the last few lectures, and this is on transition metal carbonyl complexes. Transition metal carbonyl complexes are important with regard to their applications in chemical catalysis as well as in understanding other ligands in terms of their electron donating ability. These transition metal carbonyl complexes have been used. We have spoken about these applications of transition metal carbonyl complexes in details in our previous lecture. Now, this in the last lecture we have also looked at the synthesis of transition metal carbonyl complexes and looked also at the structure of these transition metal carbonyl complexes. Now, as far as the synthesis is concerned for transition metal carbonyl complexes, what we had seen that several strategies are used, particularly of the ones that involve direct reaction of metal in its zero oxidation state with carbon monoxide, making these transition metal carbonyl complexes. The other method involves reducing transition metal salts by a reducing agent in presence of COs to produce transition metal carbonyl complexes. We have also looked at some of the structures of transition metal carbonyl complexes, and what we saw that there is a wide diversity of structures that are seen for binary transition metal carbonyl complexes. And with that discussion, we are going to start today by looking at some of the structural features of these transition metal carbonyl complexes. Now, what we had seen that transition metal carbonyl complexes, for example, in diosmium 9 carbonyl, there is a single bleaching carbonyl, whereas the same for the iron there are 3 bleaching carbonyl moieties, and these were ascribed to the small size of iron as opposed to the osmium, leading to these the different number of bleaching carbonyl moieties. So, as far as the iron is concerned, iron contains 3 bleaching carbonyls, and osmium contains a singly bridged carbonyls. So, the reason for lesser number of bridging carbonyls in osmium has been attributed to the bigger size of osmium as opposed to iron. So, what we saw in osmium in our previous discussion that this has a single bridging carbonyl, whereas the iron has 3, and that has been ascribed to the bigger size of osmium to that of iron. Now, continuing this discussion further, we are going to take a look at some interesting more binary carbonyl complexes which shows different modes of binding. For example, cobalt being a first row transition metal forms this cluster with CO4 of tetracobalt carbonyl cluster, and each of these cobalt has 2 terminal carbonyls, and the bottom one has 3 terminal carbonyls, and then there are 3 bridging carbonyls. One, 2, 3. Now, this is an example of carbonyl bridging between 2 metal center. Now, if one moves from cobalt to rhodium, and here is this rhodium 6 cluster, of rhodium 6 cluster. Each rhodium contains 2 terminal carbonyl, and there are 4 triply bridging carbonyls, which happens at this face, which has a triply bridging carbonyl, this face and the back face of triply bridging carbonyl, and this front face of triply bridging carbonyl, and this. So, this compound is an interesting one, which contains carbonyl which are bridged to 3 rhodium, and they are designated as RH6 CO16, and this sort of represents RH6 CO12 with mu 3 CO4, and these are mu 3 carbonyls. So, we see a complex structure whereby there are terminal carbonyls and mu 3 bridging. These are mu 2 types and terminal carbonyl. Now, when one goes from cobalt to rhodium, which is bigger in size, then from rhodium one goes to iridium, which is even bigger in size, we see that the formation of bridging carbonyl is completely inhabited. So, here is a iridium 4 cluster, and each of there is no bridging carbonyl at all, and each of the iridium is bound to 3 carbonyl moieties, as is shown over here. So, the take home message is that as size increases, the bridging tendency of carbonyl to bridge decreases. So, iridium complex, iridium being bigger in size, no bridging carbonyls in this. So, this is an interesting example where we can see that as the size increases, the number of bridging carbonyl decreases, and also these example uphold the different kind of bridging carbonyls that are possible, which is mu2 type, and also it can go from mu2 to mu3 type. So, that the bridging modes as seen in that compound is that one can have a terminal carbonyl which is eta 1 terminal, one can have a mu2 doubly bridging, or eta 2 and one can even have the mu3 triply bridging, where as we saw in the rhodium carbonyl cluster, that this triply bridging carbonyls was also seen. Now, these also sort of exposes the kind of versatility that these carbonyl compounds that they show. Furthermore, there is another interesting feature that this doubly bridging carbonyl can sort of exist as a equilibrium between the terminal clusters. So, the equilibrium between the double bridging carbonyl as is drawn over here. So, and that can sort of be in conjunction with this or in equilibrium with these terminal carbonyl compounds as well. This is doubly bridging and eta 1 terminal, and the perfect example of this is in this dicobalt complex, which sort of exhibits which shows both kind of bridging in dynamic equilibrium in solution, and that can be seen over here, where all the terminal carbonyls the structure containing terminal carbonyl is in equilibrium with the structure containing the bridging carbonyls, as is shown over here. Now, these two structures are in remains in dynamic equilibrium in solution. Now, and hence one can see the presence of both of the structure. Now, infrared spectroscopy is an excellent tool for monitoring or characterizing these modes of vibration, and they would be different for the terminal ones as opposed to the bridging ones. So, the bridging ones as well as the terminal ones they appear at distinct region. This one comes around 2000 to 2100 centimeter inverse, whereas this would come somewhere around 1700 to 1800 centimeter inverse. So, there are distinct region where these bridging and terminal carbonyl moieties appear, and from looking at the CO stretching frequencies is for this bond, one can ascertain how many kinds of bridging or how many terminal carbonyls are associated with the structure concerned. So, the take home message is the larger size metals prefer unbridged form terminal carbonyl, larger metals like terminal COs, and in case of larger metals the CO difficult to form, and sometimes the presence of metal bond cannot be ascertained just by proximity. Metal distance is not a proof of covalent metal interaction, and that is just maybe a constraint put in by bridging carbonyls. And for example, there is no metal bond, no Fe bond in Fe2CO9, and this is best described by this bridging carbonyl holding this 2 Fe unit, and this sort of can be perceived as 2 Fe FeCO units held by 3 2 Fe units held by this 3 CO bridging ligands. So, these three 3 mu 2 CO holds 2 Fe units together. So, these dicarbonyl distances, the Fe2CO9 dimer is held by these 3 bridging carbonyl, and here the metal metal distance distance does not mean a covalent bond. So, this is an interesting observation, because in most of the cases a bond is ascertained by the distance or proximity of the distance, but here we find example in particularly in Fe2CO9, where the distance is not a reflection of the presence of a bond, but just an artifact because of the presence of the 3 bridging carbonyl. Now, as far as the bridging is concerned, the extent of the bridging can also vary. So, what we had seen in the last example is that terminal carbonyl may remain in equilibrium with bridging. So, we had seen that terminal carbonyl remain in equilibrium with 2 bridging carbonyls, as we had seen. So, we have seen that this is in dynamic equilibrium in the cobalt carbonyl compound, and this is terminal called eta 1 terminal, and this is eta 2 bridging. Now, there is a structure which is intermediate between the two, and that is called semi bridging, and semi bridging structure means that carbonyl is not halfway through bridging between the 2 metal center, it is interacting more strongly with one center as opposed to other center. This is semi bridging. Now, these semi bridging systems are of interest, and what one finds that for Fe CO9 if one replaces 2 of the carbonyls, if one replaces 2 of the carbonyls with BP, let us say replaces COs, 2 of them with bipyridine ligand, and then the complex that would result would have the following structure. Would have the following structure, where iron is now coordinated to bipyridine ligand. So, there are, instead of 9 carbonyls, there are 7 carbonyls, 1, 2, 3, 4, 5, 6, 7, and what it happens is, under these conditions this carbonyl becomes semi bridged, because this iron is seen to interact with the pi star orbital iron is seen to interact with the pi star orbital of these CO, leading to the formation, leading to this semi bridging carbonyl in this bipyridine complex. So, what really happens is that bipyridine because of its extremely good sigma donor ability, makes iron more electron rich, and these two iron center become disproportionately unsymmetrical, and some of the electron density of the iron is removed by interaction with the vacant pi star orbital of the CO, leading it to bridge under unsymmetrical way in a semi bridging fashion. So, with this, let me summarize the developments of today's lecture. What we had done is, we have looked at the several kinds of bonding exhibited by metal carbonyl complexes, and particularly with respect to terminal and bridging carbonyl. We have looked into situations which will sort of tend to facilitate metal clusters with terminal carbonyl, and then the ones where there would be conditions for to see the bridging. The bridging carbonyl can bridge between two centers, it is called doubly bridging. We have also looked at example where carbonyl is bridging between 3 center, that is called triply bridging. And then lastly, we have looked into some examples where carbonyl can be semi bridging between two metal centers, that is, it is more strongly bound to one metal center as opposed to other, and that we saw in the latest example, where of the two metal sites, one is made more electron rich by putting a strong sigma donor ligand like bipyridine. As a result, the iron center becomes more electron rich, and then being more electron rich, it siphons off some of the electron density onto the pi star of the bridging carbonyl, making the carbonyl unsymmetrical or semi bridging in binding. So, with that I would like to conclude today's lecture, that is on transition metal carbonyl complexes, and where we have looked into various binding modes of the metal carbonyl, kind of clusters that they form. And with that we are going to conclude today's lecture, and we are going to take up some more of transition metal carbonyl complexes, their reactivity, so on and so forth in the next lecture. I thank you for being with me in this lecture, and look forward to being with you in the next lecture, where we are going to study a bit more details about transition metal carbonyl complexes and some of the other relevant complexes which we will take up in the subsequent lecture. Till then, thank you and goodbye.